Hello, class 10th physics, chapter magnetic properties of current. So today's topic is force on current carrying conductor or force on moving charge in a magnetic field. So in order to understand how that force will work and in which direction it will work, we require a certain law on the basis of which we can see in which direction um, that charge conductor, charge particle or current carrying conductor will experience force. So before coming to this, first let me introduce a law which is called Fleming's left hand law. Actually it is rule, but sometimes it is also called law. Actually it is rule. That is more precise word for this. All right, so before I'm going to tell you uh, the Fleming left hand rule, let me draw. Okay, let us suppose this is the direction of magnetic field. This is the direction of current. Both are mutually perpendicular to each other. Then they will experience force perpendicular to both in this direction. And if it is not current, then it can also be positive charge, direction of motion of positive charge. So according to Fleming's left hand rule, now why we have used this word left hand, because this diagram resembles with, if we stretch our thumb, first finger and middle finger mutually perpendicular to each other. So all of them are perpendicular to each other like this. I have to draw it like this, and it looks like broken finger, but this is due to the restriction of 3 dimension. It is a 3-dimensional diagram, but we have to draw it in 2D plane. So if index finger points toward direction of magnetic field, middle finger points toward direction of current or motion of positive charge, then thumb will show the direction of force acting on that conductor or force experienced by that positive charge, like this. So you can remember it using your left hand, and I advise uh, you to mark your thumb as F, your index finger as D, and your middle finger as I, or direction of motion of positive charge. So what is the statement of this rule? So here it is. It looks quite lengthier, but you can develop it in your own words also. If we stretch thumb, index finger and middle finger of left hand, this is important because we can do it in using our right hand also. So that is important. Of left hand, mutually perpendicular to each other. They must be perpendicular to each other. And if index finger shows the direction of magnetic field, middle finger shows the direction of current or motion of positive charge, then thumb shows the direction of magnetic force experienced by the conductor or that positive charge. So sometimes casually students say that, okay, according to this law, thumb shows force, first finger shows magnetic field and middle finger shows current. No, the rule says that it is not just like our finger shows such and such things, like this is magnetic field, so we can say this is magnetic field and this is current and this is force. No, it is not like that. Actually, there is something happening. We have placed this current in this magnetic field and it is experiencing a force in upward direction. So first there is magnetic field. So introduce this rule with starting from index finger. If index finger shows the direction of magnetic field, first there is magnetic field. Middle finger shows the direction of motion of positive charge or direction of current. If magnetic field is there, current is there, or moving positive charge is there, then there will be a force. Then thumb shows the direction of magnetic force experienced by the conductor. So actually this Fleming's rule helps us to determine the direction of force experienced by a current carrying conductor or a moving positive charge in a magnetic field. I'm repeatedly saying positive charge, positive charge, positive charge. What about negative charge? So if there is negative charge, then we have to take the direction opposite to it. Let us suppose if negative charge is moving, if magnetic field is this way, negative charge is moving this way. This is magnetic field, and negative charge is moving this way. So according to rule, middle finger shows positive charge, and if negative charge is going this way, then we will assume that corresponding positive charge is going in upward direction. And now in order to apply the rule, we have to turn our hand. So in case of negative charge, whatever be the direction of negative charge, we have to take opposite direction and then adjust our hand accordingly, and by that we can easily find the direction of magnetic force. So the title of today's topic was force on current carrying conductor or moving charge, and I came up with this rule, which is Fleming's rule, and sometimes called Fleming's law also. Now what about this force? Once again, this concept is beyond our syllabus, but remember that if someone asks about strength of that magnetic force, then magnetic force experienced by current or positive charge. Remember, moving positive charge is directly proportional to strength of magnetic field, and this force is also directly proportional to I in case of current, and this is directly proportional to charge in case of a moving charge. So keep these things in your mind also. But this is all about its magnitude, how much strength of force it will experience. But what about the direction? For direction, we have Fleming's left hand rule. So let us suppose there are few problems, and we have to find direction of force in each case. So I stand for current, B stand for magnetic field, here P stand for proton or any positive charge. We are aware about proton, and we know that it carries positive charge, and E stands for electron, and here we know that electron carries negative charge, and in the question they can write that electron is moving, and they can also say that a negative charge is moving. So just keep this thing in your mind, that here we have to deal with current, here we have to deal with positive charge, and here we have to deal with negative charge. So okay, so we are going to apply this Fleming left hand rule. Okay, magnetic field is pointing this way, so no need to worry, I have adjusted my hand accordingly. But few people will say that, oh, in upward direction there is current, and according to rule it should be force. So no problem, I can twist my hand, and now you can see magnetic field is along this direction, left to right, middle finger is going upward, and thumb is pointing into the page. This direction will not be called downward, but it will be called into the page. Upward is this side, downward is this side, and this is out of the page, and this is into the page. So see, first align your index finger along magnetic field, then align your middle finger along the direction of current, and automatically thumb will point out into the page. So direction of force will be into the page. This is direction of force into the page, into the plane of the paper. Next time I will write inward or outward. Okay, second case. Now magnetic field is going downward. So first I align my index finger downward, and then current is going that way from left to right. So thumb will point into the page. Once again, it is coincidence that it is again going into the page. Here I is denoted by a dot. Dot means it is coming out. So current is coming out. First magnetic field. Magnetic field is this way, and current is coming out. See, First align index finger along magnetic field, and current is coming out, not the force, current is coming out. So arrange that this way. And now what is the direction of thumb? That is upward. So it means it will experience force in upward direction. Oh, here inward, here upward. Okay, I'm leaving this for you. Okay, similarly for proton, proton is a positive charge. If it is moving this way, no need to worry, we will directly apply Fleming rule, and first align index finger along magnetic field, that is upward, and automatically, we need not to worry about this, it is automatically came along the direction of positive charge, so direction of force will be outward. This is called outward. With black color I am writing direction of force. I have mentioned it here, so I am not mentioning it otherwise elsewhere. So now magnetic field is this way, positive charge going downward, so direction of force, it is directly we are able to do this, it is coming outward. Here positive magnetic field is going downward, and positive charge is also along this direction, so once again force is coming outward. Okay, here magnetic field, cross means inward, so magnetic field is going inward, and positive charge I have to align it this way, and now thumb is pointing downward. Okay, for electron or negative charge, you have to be very careful. First align your index finger along magnetic field, that we have to do in each case, and see, electron is going this way, but we have to take opposite direction because electron is negatively charged, and rule says we have to take positive charge. Here we have negative charge, so we will reverse its direction and assume that it is positive charge. Reverse the direction, it is positive charge. This and that. So direction of force is inward. Okay, magnetic field this way, electrons are going downward, but according to rule we have to change the direction, and once again direction of force is inward. And see, I have just copied the diagram from here, and you can see for positive charge it was coming outward, and for negative charge it is going inward. So also here it will come out, it will also go inward. This is our prediction. Let's check it out. First align your index finger along magnetic field, but we are not going to take this as direction of electron, because we have to consider positive charge. So in order to understand this, oh god, I'm twisting my hand a lot. Now electron is going this way, so we will assume a positive charge is going that way. Now thumb is pointing inward. And finally, electron is going this way, magnetic field is going downward, so first we align, magnetic field is going downward, electron is coming this way, so corresponding positive charge is going that way, so direction of force is upward. So this is how we will do it. This is for as a practice problem for you people, and now a trick question for you people. This is magnetic field, and a neutron is going this way, so what will be the direction? That's all for today.